NEC Section 310.15b3 addresses the ampacity adjustment required when multiple conductors are installed in a single raceway. This directing is essential to account for the increased heat generated by bundling conductors together. Running parallel feeders in the same raceway can potentially increase the voltage drop compared to running them in separate raceways. This is because the magnetic fields generated by the parallel conductors can induce opposing currents in each other, resulting in a higher overall impedance. The close proximity of parallel conductors in a single raceway can create electromagnetic interference, EMI, which can interfere with sensitive electronic equipment connected to the UPS. It is generally considered best practice to provide separate raceways for parallel feeders. This minimizes voltage drop and reduces the risk of EMI. If separate raceways are not feasible due to space constraints or other reasons, consider oversizing the single raceway. This provides more space for heat dissipation and helps to accommodate the parallel feeders without excessive directing. Shielded conductors can help reduce EMI, especially when conductors are in close proximity to each other. Using shielded conductors can mitigate the potential for interference with sensitive equipment. When installing parallel conductors, you must adhere to NEC directing requirements. Table 310.15b3 provides the adjustment factors based on the number of current-carrying conductors in a raceway or cable. Failure to properly direct conductors can lead to overheating and potentially hazardous conditions. Firstly, calculate the ampacity of each conductor based on the load requirements. Secondly, determine the number of current-carrying conductors in the raceway. Thirdly, consult NEC Table 310.15b3 to find the appropriate directing factor. Fourthly, multiply the initial ampacity by the directing factor to obtain the adjusted ampacity. Fifthly, ensure that the adjusted ampacity is sufficient to carry the load current. When using parallel conductors, each conductor must be sized to carry its proportional share of the total load current. The conductors must also be of the same length, material, and insulation type. The termination points of the conductors must be properly torqued and tightened to ensure a good electrical connection. Using separate raceways helps to minimize the effects of circulating current. Circulating currents can occur when the magnetic fields of the parallel conductors interact, leading to increased losses and potential overheating. Separating the conductors reduces the magnetic coupling and minimizes the flow of circulating current. Proper grounding is essential for minimizing EMI and ensuring the safe operation of the UPS system. Grounding conductors should be properly sized and connected to a common grounding point. Shielded conductors, if used, should be properly grounded to provide effective shielding. Regular inspection and maintenance of the electrical system are crucial for identifying and addressing potential problems. Check for loose connections, damaged insulation, and signs of overheating. Periodically test the UPS system to ensure that it is functioning properly and providing the required power quality. The use of harmonic filters can help to reduce harmonic distortion in the electrical system. Harmonic distortion can be caused by nonlinear loads, such as electronic equipment, and can lead to overheating and equipment malfunction. Filters help to mitigate these effects. Power quality analyzers can be used to monitor voltage, current, and other electrical parameters. These analyzers can help identify power quality problems, such as voltage sags, swells, and harmonic distortion. Monitoring these parameters allows for timely corrective action to be taken. When installing parallel conductors in a single raceway, it's essential to carefully consider the potential impact on voltage drop, electromagnetic interference, and heat dissipation. By following best practices and adhering to NEC requirements, you can minimize these issues and ensure the reliable and safe operation of the UPS system. Also, ensure all conductors are of the same gauge, for example 4/0, 250 kcmil, 350 kcmil, 500 kcmil or 750 kcmil. The conductors must be made from the same metal, such as copper or aluminum. The insulation must be rated for the correct temperature rating. For example, THHN, THWN, or XHHW. The insulation must be rated for the correct voltage rating, for example 600 volts. The raceway must be sized appropriately for the number of conductors installed in it, as per NEC Chapter 9. Conduit fill calculations must be performed to ensure that the raceway is not overfilled. The raceway must be properly supported and secured. The raceway must be protected from physical damage. The raceway must be installed in accordance with all applicable codes and regulations. The NEC contains tables that dictate the number of conductors allowed in specific conduit sizes. These tables take into account the conductor size, installation type, and conduit type. It is crucial to refer to these tables and perform calculations to ensure that the raceway is not overfilled, which can lead to overheating and difficulty in pulling conductors. When using parallel conductors, it's important to maintain proper spacing between the conductors within the raceway. Unlinked conductors too tightly can impede heat dissipation and increase the risk of overheating. Using cable ties or straps to loosely secure the conductors can help to maintain spacing while keeping the conductors organized. Consider using a larger raceway than initially planned to provide extra space for conductors and improve heat dissipation. This can be especially beneficial when using a single raceway for parallel conductors, as it helps to mitigate the effects of bundling. Selecting conductors with higher temperature ratings can help to improve their ability to withstand heat buildup. Conductors with ratings such as 90 degrees Celsius may be suitable for applications where heat dissipation is a concern. When making connections to terminals or equipment, it is crucial to use properly rated and sized connectors. Ensure that the connectors are compatible with the conductor material and size, and that they are properly torqued to ensure a secure and reliable connection. Using torque wrenches to tighten connections to the manufacturer's specifications helps to prevent loose connections and overheating. After installation, perform a thorough inspection of the entire system to identify any potential problems. Check for loose connections, damaged insulation, and signs of overheating. Use a thermal imaging camera to detect hot spots, which can indicate areas of concern. It is important to document all aspects of the installation, including conductor sizes, raceway types, rating calculations, and inspection results. This documentation can be valuable for future maintenance and troubleshooting. Establish a regular maintenance schedule to inspect and test the system. This includes checking connections, measuring voltage drop, and monitoring temperature. Periodic testing can help to identify potential problems before they lead to failures. Remember that the specific requirements for parallel conductor installations can vary depending on the application and local codes. It is always best to consult with a qualified electrical engineer or inspector to ensure that the installation meets all applicable requirements and best practices. When selecting conductors, consider using conductors with low smoke, zero halogen LSEH insulation. LSEH insulation produces less smoke and fewer toxic fumes in the event of a fire, which can improve safety and reduce damage. When using a single raceway for parallel conductors, consider using a raceway material with good thermal conductivity, such as aluminum. Aluminum raceways can help to dissipate heat more effectively than PVC or other non-metallic raceways. Consider using a forced air cooling system to help dissipate heat from the raceway. This can be particularly useful in applications where the raceway is located in a confined space or where ambient temperatures are high. Use surge protection devices, SPDs, to protect the UPS system from voltage surges. Voltage surges can damage sensitive electronic equipment and disrupt the operation of the UPS. SPD should be installed at the service entrance and at the UPS input. Proper labeling of all conductors and equipment is essential for safety and maintenance. Clearly label all conductors with their circuit identification and voltage. Label all equipment with its function and rating. Proper coordination of overcurrent protection devices, OCTs, is essential for ensuring that faults are cleared quickly and safely. OCTs should be selected and coordinated to minimize the impact of faults on the electrical system. Harmonics are currents or voltages with frequencies that are integer multiples of the fundamental frequency, which is typically 60 Hz in the United States. Nonlinear loads, such as electronic equipment, can generate harmonics that can distort the voltage waveform and cause problems such as overheating, equipment malfunction, and interference with communication systems. There are several methods for mitigating harmonics, including using harmonic filters, reactors, and transformers. Harmonic filters are designed to block or reduce the flow of harmonic currents. Reactors are used to increase the impedance of the electrical system to harmonic currents. Transformers can be designed to block certain harmonics. Power factor is a measure of how effectively electrical power is being used. A low power factor indicates that a significant portion of the electrical power is being wasted. Improving the power factor can reduce energy costs and improve the performance of the electrical system. There are several methods for improving power factor, including using capacitors, synchronous motors, and active power factor correction devices. Capacitors are used to provide reactive power to offset the reactive power consumed by inductive loads. Synchronous motors can be operated to provide reactive power. Active power factor correction devices use electronic circuits to actively control the flow of reactive power. A voltage sag is a temporary reduction in voltage, typically lasting from a few cycles to a few seconds. Voltage sags can be caused by faults in the electrical system, motor starting, or other events that draw a large amount of current. Voltage sags can cause equipment to malfunction or shut down. There are several methods for mitigating voltage sags, including using uninterruptible power supplies, UPSs, static var compensators, SVCs, and dynamic voltage restorers, DVRs. UPS provide a continuous source of power during voltage sags. SVC provide reactive power to support the voltage during sags. DVR inject voltage into the electrical system to compensate for the sag. A voltage swell is a temporary increase in voltage, typically lasting from a few cycles to a few seconds. Voltage swells can be caused by switching operations or other events that cause a sudden increase in voltage. Voltage swells can damage sensitive electronic equipment. There are several methods for mitigating voltage swells, including using surge arresters, transient voltage surge suppressors, TVSSs, and active voltage conditioners. Surge arresters and TVSSs clamp the voltage to a safe level during swells. Active voltage conditioners regulate the voltage to a constant level. Transient voltages are short-duration, high-amplitude voltage spikes. Transient voltages can be caused by lightning strikes, switching operations, or other events that generate high-frequency noise. Transient voltages can damage sensitive electronic equipment. There are several methods for mitigating transient voltages, including using surge arresters, TVSSs, and filters. Surge arresters and TVSSs clamp the voltage to a safe level during transients. Filters block high-frequency noise. Electrical noise is unwanted electrical signals that can interfere with the operation of electronic equipment. Electrical noise can be caused by a variety of sources, including electromagnetic interference, EMI, radio frequency interference, RFI, and ground loops. There are several methods for mitigating electrical noise, including using shielded cables, filters, and proper grounding techniques. Shielded cables block EMI and RFI. Filters block unwanted noise signals. Proper grounding techniques prevent ground loops. The grounding system is an essential part of the electrical system that provides a path for fault currents to flow back to the source. A properly designed and installed grounding system can protect people and equipment from electrical shock and damage. The grounding system should be designed in accordance with the NEC and other applicable codes and standards. Regular inspection and testing of the grounding system are essential to ensure that it is functioning properly. Consider the use of fiber optic cables for communication signals, as they are immune to EMI and RFI. Fiber optic cables can provide a reliable and noise-free communication link between different parts of the UPS system.